Hello again, and welcome back to another lecture on the galactic foreground emission mechanisms as a part of the cosmological component separation course. This lecture will be focused on anomalous microwave emission, which is otherwise referred to as AME. As always, we'll start by first refamiliarizing ourselves with the microwave foreground gallery, and this lecture will be focused on the orange line here, which is labeled spinning dust emission. You can see that it is one of the three strong foregrounds below 70 gigahertz, and it is important, therefore, to understand this emission mechanism to be able to disentangle it from the other two strong emission mechanisms here. If at the end of this lecture you are still curious about details about AME theories and predictions, please check out the State of Play of Anomalous Microwave Emission Research, which is written by Dickinson et al. And all these other wonderful authors who have spent many years working with AME theories and predictions and observations, setting constraints and stuff. I dubbed this paper the Holy Grail of AME information, so if you find yourself more interested, please check out that paper. An outline for this lecture will have us first look at the history of the AME and why it's named such, the spinning dust theory and some of its predictions, and other potential models for AME. The anomalous microwave emission is named this simply because this is what it was first dubbed as when it was discovered when analyzing the COBE and WMAP data sets. It was an unexpected foreground to be discovered when analyzing these data sets, as synchrotron, free, and thermal dust emission had all been expected, and this appeared as a bump, as an enhancement to the thermal dust spectrum because of the strong correlation with dust emission morphology on the sky. And this dust-correlated emission peaks at around 15 gigahertz and is strong between 10 and 60 gigahertz. The general idea here is that this emission is due to spinning dust grains, and these grains will be spinning in the ISM due to collisions with gas atoms and other processes, and if these grains have an electric or magnetic dipole moment, then they will radiate while they spin. With power given by the Larmor formula shown here. Practically, the frequency of this emission is given by this formula here, which shows that it's strongly dependent on the temperature, the density of the grains, as well as the size of the grains. And in order to get the dust spinning at 20 to 30 gigahertz where we observe it, the grains have to be very, very small, less than 1 nanometer in size. The actual shape of the SED is expected to vary with the gas environment, as shown in this plot from the AME, the State of Play AME paper. We also expect it to depend on the particle size, the charge states of these particles, and the dipole moments of these particles. And we honestly don't have a lot of knowledge a priori of how each of these properties of these nanoparticles should vary throughout the galaxy and what we expect them to be, as observational windows into these very small dust grains are rare given their small size. But if we're able to actually identify AME regions and check SED variations, then it will be very useful to help us understand exactly what the environments for these grains looks like. And again, we always want to bring things back to polarization because that's our main concern here. So is the spinning dust polarized? Just like with the thermal dust emission, if these grains are oblate or prolate and are aligned with the magnetic field, we expect this emission to be 100% polarized. And with big grains, just like with thermal dust emission again, we expect that dissipative processes will bring the angular momentum vector into alignment with the magnetic field vector. But looking at Huang et al. 2013, where they have kind of walked through the spinning dust model and made some predictions, you can see that the expected level of polarization just by eye is less than 1% here, so not very polarized at all. This is really due to the grains being very, very small. And as such, it's very easy to kick these grains back out of alignment. Additionally, we need to think of these grains not just as the classical particles, but also as quantum mechanically, because they're simply so small. And alignment requires converting the rotational kinetic energy into thermal energy. This is the dissipative process we were talking about before. But rotational and vibrational states for particles this size are quantized. And walking through the physics of treating these particles quantum mechanically has shown that we really do not expect a significant level of polarization for spinning dust emission. The observations seem to agree with this. Large-scale constraints on the polarization were done by Massalari in 2011 when going through the WMAP 9-year data, and found that it's less than 5% polarized at 23 gigahertz, while Herman 2021, which is currently in prep, has found that the large-scale polarization is less than 1.7% between 20 and 60 gigahertz. And there's also a host of small-scale polarization constraints that have been set within different regions in the sky, such as the Perseus region, some molecular complexes, and the Taurus molecular cloud, all which seem to agree with the Massalari constraint of definitely less than 5% polarized on, and even less than 1% polarized on small scales. So now let's talk about some alternative models that aren't the spinning dust model. So first we'll talk about the magnetic dust model and some other emission mechanisms. So magnetic dust model is essentially the idea that these small grains will have iron inclusions, some iron atoms in there, similar to chocolate chips in a chocolate chip cookie, where some of these iron inclusions may appear as ferromagnetic inclusions, where they become aligned with the local magnetic field. If this is the case, then we would expect some strong millimeter emission and even some possible radio resonances to appear as the emission mechanism here. There would be, if this is the case, we would expect a very distinct signature, such that the dipole emission is orthogonal to the typical electric dipole emission that we would expect from the spinning dust model, for example, or even the alignment of the thermal dust grains would be orthogonal to this emission as well. But is this even possible? I mean, it's hard to get an AME-like spectrum generically to fit as resonance behavior, as we saw two slides ago here. You see on the far right-hand side of the plot, these bumps are possible radio resonances. It's difficult to get these generically, as it depends on specific shapes of grains. And the big thing here is that if it is magnetic dust, we would expect strong polarization. There is possible magnetic dipole emission as a subdominant component of long wavelength emission, but is unlikely to give the AME bump, which is so characteristic and what really allows us to see this emission. Other mechanisms, there's the possibility of optical properties in grains that just have a feature at these wavelengths, and there's also the possibility of a two-system model that has been suggested by Jones, 2009. But again, the big issue with both of these is that if there are these large grains, then we would expect strong polarization. As a summary, AME emission has a strong correlation with thermal dust emission, and it appears that the spinning dust model is to be the most consistent both in total intensity and polarization as an explanation for AME. The spinning dust SED is expected to be highly variable given its susceptibility to different properties, so being able to investigate smaller regions where the SED is clear can really help us give some insights into the properties of the environment and the properties of these grains. Also, and is probably good news for CMB science, is that both theoretical arguments and good observational constraints have shown that we can likely have negligible polarization for spinning dust emission. Thank you very much.